Good morning, guys. Today we're going to discuss interpreting chemical equations. So basically, we're in section 12.1 of your textbook. You should have already created your pre-notes for 12.1 and as your prep work, and now you're going to actively watch, making sure to stop, pause, and rewind where you need to. Don't forget that when you're done, you'll need to write a summary at the bottom of your pre-notes of the video, and also make sure that you go online and answer the question of the day. So, interpreting chemical equations. The study of this is called stoichiometry. So when you're reading your chapter 12, there's this very long word that looks kind of scary, and the word is stoichiometry. No one expects you to say it perfectly, but so many students ask what it means. And basically, it's the study of how reactants relate to products. So we do this all the time. When we are making corn muffins, for instance, from the box, it'll say add a half or maybe a third of cup of milk and an egg in order to make those corn muffins. That's going to give us 6 corn muffins. So we know that there's a 1 egg to a third cup of milk to 6 corn muffins as our product ratio. If we wanted to make 12 corn muffins, we now know that we need twice as many eggs and twice as much milk in order to make my 12 corn muffins. So that's pretty much what stoichiometry is. The only difference is we're not using the back of the box. We're using our chemical equations for our recipe, if you will. So I'm going to show you an example, and remember to feel free to pause, stop, and rewind if you need to. So at the top of the board you see an equation. It says iron plus oxygen gives you iron 3 oxide. We've discussed in previous videos how we come about to get that particular equation. Today what we're going to discuss is how this works out in terms of the recipe. So we can see that if we wrote the balanced equation, iron is a non-diatomic element, so it's just Fe. Oxygen is diatomic, so it's O2. And iron 3 oxide is ionic compound, so that's how we get the Fe2O3. The Fe has that 3+ charge that's in the Roman numerals, and the O, we figured that out from the periodic table, it's 2-. Once we balance that, we have coefficients of 4, 3, and 2 for those going left to right. So this particular equation tells us that for 4 atoms of iron, we can get we'll need to combine that with 3 molecules of O2 in order to form 2 formula units of FeO3. Now, for some of you, you're trying to figure out the difference between atoms, molecules, and formula units. Basically, the term molecule is used for things that are more than one atom and covalent, so like O2 or CO2 or water, whereas formula units are used for formulas that are ionic. Not going to give you a test on that or anything, but just know that molecules are used for one and formula units are used for the other. If you were to mix up molecules and formula units, I wouldn't count you wrong. Well, here's what's even more important in this, is that 4 atoms is really, really small, and it's impossible for us to see with the naked eye. So typically when we measure things, we measure them in moles. So 4 moles of Fe can combine with 3 moles of O2 to form 2 moles of Fe2O3. If we were to use the periodic table to figure out the mass of those things, we now have 223.4 grams of iron. And that comes from taking 4 times the approximately 56, I think it's 55.6. Look at your periodic table for iron. 3 times 32.0, that's where they get the 96 from. And that's going to give us 2 moles of iron 3 oxide. So if we know the molar mass of iron 3 oxide and we multiply it by 2, that's where this number is coming from. Remember, all of our molar masses come directly from the periodic table. I also want to point out that the law of conservation of mass is observed here, meaning that the mass of our reactants is the same as the mass of our products. We didn't lose anything. Nothing was created, and, well, a substance was created, but in terms of we didn't create new mass and we didn't destroy new mass. So notice that if we were to add these 2 numbers together, we get 319.4 grams of reactants total, and that's equal to 319.4 grams of products. What I suggest you do is to pause right now, rewind, and go back and listen to this entire talk again so you can see how these numbers actually relate to the individual things that are being asked. So now we're going to talk about mole ratios. Typically when we're in the lab, we're not combining perfect amounts of moles. We're not getting exactly 4 moles. It might be 4.5 or 7.3 or 2.79. So we're going to have to learn to convert those. Before we learn to convert, we need to learn the conversion factor. And the conversion factor is called the mole ratio. The mole ratio comes directly from this equation here. I'm going to show you in the next board. So what we can see here is the exact same equation. We have 4 irons plus 3 oxygens gives us 2 iron 3 oxides. Keep in mind here that we have one ratio, 4 moles of iron for every 3 moles of O2. Those numbers come directly next to what it's in the equation. So iron is next to a 4, it stays next to a 4. The only difference is we shove in moles in the middle. Same thing for 3. And because a ratio is typically between 2 things, because we want it to be something that we can plug into an equation and make into a fraction, we just compare 2 things, iron and oxygen in this case. Now, we can look at it as an iron and oxygen ratio, or we can look at it as an oxygen-iron ratio. So we also have the 3 to 4, 3 moles of O2 to 4 moles of iron. Likewise, we can compare 2 different things. We now can compare iron and iron oxide. That's where we get the 4 moles of iron to 2 moles of iron oxide. Again, these numbers stay in the exact same place. The only difference is we're sticking mole in the middle of them because it is a mole ratio and we're comparing moles. Here we have 2 moles of iron oxide to 4 moles of iron, which is exactly the same ratio, it's just flipped upside down. Now the bottom of the board may be a little bit hard to see, but what I've basically done is looked at 3O2 and 2 Fe2O3. So 3 moles of O2 for 2 moles of Fe2O3, 3 moles of oxygen for 2 moles of iron 3 oxide, and the reverse of that, 2 moles of iron 3 oxide for 3 moles of O2. Now, as a part of your notes tonight, well, first, what I need you to do is I need you to rewind this back and play this again so that you can understand where each of these come from. But part of your notes for tonight is that I need you to try this problem. So you have 2 nitrogen plus 3 hydrogen gives you 2 ammonia in H3. What I'd like you to do is to take this and express it in terms of molecules, moles, and mass. Molecules, moles, and mass. Now I already did that earlier in a different slide. So if you rewind and go back to the information in terms of the iron problem, the very first time I showed you the iron equation and how I worked that out, you'll be able to actually see how to solve this particular problem. Then what I'd like you to do is to do the same thing, but now write the mole ratios. So go back to that iron problem, see how we wrote the mole ratios for that iron, oxygen, iron 3 oxide problem, and see if you can apply it the same way. When you come to class, next class, have this problem already solved. When you come, we'll work with this problem and from there figure out what your needs are and how I need to work with you. Do not forget to try this problem. Do as much as you can. Write down the problem, set it up. If you can't figure out what numbers go where, set it up as much as possible, and I'll help you the rest of the way when we come to class. Don't forget to answer your WIS question. Don't forget that if you have not annotated your notes, you need to go back, replay this entire video, and annotate those notes. And don't forget to write a summary of this video at the bottom of your pre-notes. See you guys soon. Bye.